Hello everyone! How's everyone doing today? Alrighty, we're coming back to Zig. Yeah, so last time we went through memory and allocators. We learned, I wouldn't say all about it, but a little bit about it, just to have an idea of how to use it. So today we're gonna focus on the first project from the book, building a base64 encoder and decoder. But before we go and dive into that, let's just look into our Ziglings and see if we can kind of get a quick refresher by completing a few of those. So I know that we went through while loops, we went through for loops, the quiz, and then did we do functions? I don't remember. Return 42, yes, we did functions. We just didn't do errors. But because we have a bunch of other things like, the for keyword, the switch statement, all the things that we actually kind of went through already. So let's just have like an overall quick overview of errors and Zig through Ziglings. This way, I believe it will be a little bit easier to understand all the additional all the further stuff in the book as well, because we already saw a lot of stuff with, like exclamation marks here or there to kind of signify errors. We saw the try keyword. So it'll be nice to have a little bit more, at least like basic knowledge about it instead of just guessing nonstop. So, alrighty. So, exercise 21. Believe it or not, sometimes things go wrong in programs. Never expected that. In Zig, an error is a value. Errors are named. Okay, so error is a value. Does it mean that it's just... Okay, so I guess it's not anything special, right? Some languages try to make errors into something special that has its own entire chain of how things are going. Here, error is just a value. Errors are named so we can identify things that can go wrong. Okay. All right. So they're named so that we know what happened, right? Errors are created in error sets, which are just a collection of named errors. Okay. So we have concept of error sets. I understand this means that, it's common that an error happened and we have several reasons for it. I mean, the first thing that comes to my mind is like, okay, we made an API request, or like we received it and we need to verify several things. And instead of just throwing an error on the first thing that went wrong, maybe we verify all of them and return a set of errors that went wrong. Wonder if that's the case, or maybe as we're handling things, we're tacking on like additional ones. I don't know. This is interesting. We have the start of an error set, but we're missing the condition too small. Please add it where needed. So a constant my number error, and okay, so we define error by making a struct that just has error in front of it. Okay, too big, something, 2.4. 2.4, that's funny. Too small. Right, we fixed that. And what happens next? We just get a std, we have main, numbers, so we have a list of numbers, array of numbers, whatever. We iterate over them and we just print, hi, this is a number error, so number fail. So this is a separate function. Okay. So what number fail does, it returns my number error, which is this type that we define here that is supposed to be an error. Okay, so, so this is the function that is supposed to fail, right? Because it returns an error, but it always returns it, right? If this return that, if that returns too small, and this one is just whatever. Everything else is 2.4, right? It will always return an error. Great. So we can capture an error in this style, which is, we just received an error. And then if error is too big, we print this. If error is, I guess, too small, if a number error is my number error too small, and there we go. And otherwise, print this one. Okay, so we're not doing really error handling here other than receiving it and that's it. Oh, look at that. What compiler is concerned about is that this is type of error. Well, here we specified my number error, but compiler here just shows like, hey, or not compiler, the LSP just sees like, you know what, this is really error, just error, nothing else. Even here, it returns error. Okay, so we lost the info about the type, even though we're explicit. That is unexpected. Okay, all right. Oh well. Great. So that's it, right? We can run it. So it'll be zig run 021. And yep, we got a whole bunch of numbers, no errors. Great. As in program compiled. So let's move forward. A common case for errors is a situation where we're expecting to have a value or something has gone wrong. Take this example. Bar text. So we create text variable, which type is supposed to be text. We do get text, whatever. What happens if get text can't find foo.txt? How do we express this in Zig? Zig lets us make what's called an error union, which is a value which could either be a regular value or an error from a set. So text is my error set, exclamation mark text. Ooh, really? We start with an error, exclamation mark, I guess, is that syntax that divides it? Looks very strange, but maybe that's the hint. Where maybe we use the exclamation mark to always just say that, hey, this is supposed to be error. Everywhere you see an exclamation mark, it will always mean it's an error. That's a pattern I'm starting to see. CPN says hello. Hello to you too. How are you doing? Already, I mean, I like it. It's kind of like Go, right? For now, let's just see if we can try making an error union. So we get our std and my number error. Error too small, right? So my number is type of, well, it should be an integer, but I guess the idea here is that it could be either my number error, instead of just pi for or, we just do exclamation mark, and normal will be whatever, I32, right? Or whatever it's supposed to be. Okay, all right. Looks like my number will need to either store a number or an error. Can you set the type correctly above? Yes, we did. And there we go. It should work. Let's go number 22, and it compiled. I compiled. Great. Cool. I kind of like that. It's very strange with that exclamation mark in the middle, but hey, whatever. At least we know that, I guess, the thing on the left is always supposed to be an error. What if I'm going to flip it? Can I just flip it? Does it mean that this is supposed to be error now? Does it matter? No, expected error set type found I32. Okay, so basically the compiler will check that if the left of the exclamation mark is some kind of error struct or whatever it is. Okay. Sven says, did you see the message I sent you on Discord? Oh, I recall there were a few messages. I was like super busy. But I saw them. I didn't read them. Let me double check, because I recall seeing like, oh yeah, I need to go through that. Yeah, the job search basically was like all encompassing, and I got a job, so now I can start relaxing and getting back to having a life. It's funny when not having a job means you have less time than when you have a job. Okay, I can see you send stuff up a recursion and a lot about. Okay, error handling 101. Let's load this up. Load up your error handling 101. Let me just go here and drag it over. General, there we go. Let's plop it here. Maybe literally just a third screen. There we go. Okay. All right. So Zig error handling 101 by our frequent visitor, CPN. You can think of errors as a parasite that is attached to the return value of a function. We need to get rid of the exclamation mark that's been clinging onto our data to use the data. Yep, there we go, exclamation mark. Yep, that's the pattern I'm seeing. Whenever we have exclamation mark, it means there's something with an error. For example, let's say we have this function. Only odds, and we have exclamation mark U32. So what I learned so far looking at this thing, suddenly tells me we can just omit this one. And therefore we have a situation where this could be any kind of error or U32. That's a fun syntax. All right. So only odds is this, right? It could throw an error. So return if ampersand. It's not 0. Oh, okay. Ampersand is some kind of modulo or something. I don't know. This is interesting syntax. Then else error even number. Okay, so instead of returning a boolean, we just okay, we either return the odd number or we just throw an error. Okay, makes sense. We kind of use the return value as is due to type mismatch. Pretend like this value is given by the user via CLI args or standard input or whatnot. Yeah. Constant n is 32, right? Then we have odd n is only odds, right? But that returns U32 or an error. So this won't work because the type of odd n is exclamation mark U32, not just U32, right? We can't just print this plus 9 because we don't know what is error plus 9. SPN says, yes, that's correct, or n, and then we have ampersand 2. Percent 2. So this is interesting because when I see and like that, it suggests some kind of bitwise and operation. And I guess because this is just one last bit, we either have that the one bit is true, which is even, or not, which would be not even. Therefore, if we put 0 here, we'll be matching for even numbers. If we put 1, we're going to be matching for uneven numbers. Huh, never thought about that. I guess that's the fun with bitwise operations. Cool, that's cool. Nice. Yeah, bitwise operations is a world I just don't like touching for some reason. It's equivalent of regexes for me. I think I even prefer regexes than binary math. All right. So we understand this. One way to get rid of is using catch. So we have our constant here. If the function returns an error, odd n, will be whatever it is on the other side of the catch keyword. So constant odd n is only odds and catch plus n plus 1. Oh, okay. So basically, if this throws, returns, it's no throwing. If it returns an error, we have a chance to catch it and just say, hey, this is a default value, basically. Okay, I see. This is, wow, very interesting concept. Huh. All right. And now it will work, of course. But that resorts that we just have a default value that we can calculate on the go. All right. And I presume there's some additional syntax to actually catch the error value, or maybe not. This is a good place to use that labeled block expression thing if you want to do some stuff like logging, right? We have our constant, and then odd n is on the odds, and if we catch, we just create a blank new, what do you call it, block. And we just say, hey, warn modifying the value to fit the needs, and we break this thing by returning, and basically this block will suddenly return this value. So yeah, this is a syntax that's worth remembering and practicing. Okay. And then we print the stuff because here we already have the n to be always U32. And CPN says the bit is more efficient. Yeah, I definitely agree because there's no extra calculations. Basically, the modulo probably needs to perform several operations to get the value for whatever the inputs are. While, where was it? Well, this is probably more efficient because this is just one operation by the processor. Hey, bitwise was the result, and then maybe a check or a jump. So yeah, I like that. I wonder if the compiler, if it sees modulo 2, just compiles it away anyway. I wouldn't be surprised. Okay, so we've got those, great. I like the block. Or if you want to exit the function when you encounter an error, you should do this instead. Yep, catch and return. There we go. Though it will be nicer to return the error to let the user know what happened. So by the way, this is how we capture the returned error. There we go. We capture it in this capture group, as I would call it. I think I recognize it mostly from Rust, maybe, where there were those capture groups for like scopes and whatnot. So I guess the pattern is used here, so why not? So yeah, we have the thing, catch, and we catch the error and return the error, for example, to propagate it outside. Okay, and try is just the shorthand version of the snippet above. Oh, okay, so try something means that we instantly return it. Oh, so we instantly return it. That's interesting. Okay, all right, I can see it working. Also, you can unwrap the error later at any point. So, somewhere up there, we can no problem go and try odd n plus 9. Oh, and if this will fail, try will just make it return before we even execute the print. Okay, all right. Makes sense. It's common to use switch along with catch to handle different errors differently if the function returns more than one error. Okay, so function only tiny odds, right? So again, we have the same error possibility. If it's larger than 256, return error too big. Otherwise, return only odds. Whatever, return try only odds. Okay. All right, so this would propagate the error out. Do we need the return here then? I guess yes, we need to return because we return either the valid value, wow, or if there's an error, the try will just skip the return and return on its own. Okay. All right. So we've got usage of it will be more and more text, more and more code. So only tiny odds, right? We catch the error and then switch over the error. And maybe if it's a given number, we do one thing. Yep, we can return some value that's gonna be here. Or maybe some other switch statement, right? Alternatively, you can do this if you just want to set the value and do nothing else. So error even number is this, right? Yep, we just set the default value, and if we have something else, we can even do panic and just break the whole program. All right, and we can use else here as a catch-all for all the other errors, but we don't need here because, we handled them all, but I guess there would be a possibility that we actually return a different type of error, and I guess type inference would take care of it for us and throw an error like, hey, you haven't handled this other weird error. So yeah, great. Okay. And then we have full code with all the examples, right? Or like those two combined. Okay, that makes sense. And then we have video and recursion, which I'll check out later. Thank you for that. This was really nice. This was really nice. So now I have a little bit more understanding of all the ways to do with errors. So now probably we're just gonna storm through all those errors. So yeah, let's see. We had this situation with the exclamation mark. We did that, it compiled, great. Let's move on to number 3. One way to deal with error unions is to catch any error and replace it with default value. So there we go, we have the catch. Food that can fail, catch, and if it failed, we catch and return 6. So if can fail fails, food will equal 6. And we have the exercise, we have our number error. Okay. And then we have our main function, we have add 20, catch 22. Okay, so add 20 will do something, right? If it's less than 5, it will return error too small. Otherwise, it's just going to add 20. Okay, so we have 44, catch 22. We know that this will never throw, but we can just catch it just in case. And here, if it's 4, we definitely need to catch it because we know that implementation will just throw an error. Okay, and there we go. And here we just need to return the my number error, exclamation mark U32. And that could work, or I presume we could just skip it. I guess, I don't know, maybe. That's what it suggests so far. So Zig run 023, and it worked. Alrighty. So errors 4. Let's just close all the other ones. So 24. Using catch to replace an error with a default value is a bit of a blunt instrument, since it doesn't matter what the error is. Catch lets you capture the error value and perform additional action with this form. So can fail, catch the error, and we do something with it, right? Okay. Alrighty. So if error is something, do something. So looks like we can just start a new block. I don't think we need to do the label. Unless with a label we just have extra features of doing break and whatnot. Okay. So we've got import, my number error, great. So the error is just a list of 2 random strings. So was it how we create enums? I already started forgetting so much. I guess we're gonna go through enums in a short moment. Okay. All right. And then we do basically, hey, the catch 0 below is a temporary hack to deal with make just writes return error union for now. Okay, so this is just, whenever we have error, we just throw 0. I mean, return 0, right? Standard this and that, great. In this silly example, we've split the responsibility of making a number just right into 4 functions. Make just right, fix to big, fix to small, and detect problems. So make just right. So this is going to return fix to big. And we catch the error, which could be too small or too big. Oh, now I understand the set. Okay, so this is the error is set of those little values that we can specify, like little labels and whatnot, just names, I would say. So just names, I could even call them symbols, right? Because they don't have a value of their own. They just are labels. Okay, interesting. And therefore, I mean, there must be a way to add some extra data into that. There must be a way. But okay. All right. And therefore we see that, hey, the error could have a value of too small or could have a value too big. And that's how we can switch over them. Okay. Makes sense. So fix too big will be, again, error of this. Do that. Return 20 if number is too big. Otherwise, return the error. Fix too small. Oh dear, this is missing a lot, but don't worry, it's nearly identical to fix too big above. If we get a too small error, we should return 10. If we get any other error, we should return that error. Otherwise, we return a U32 number. Okay, so return detect problems, catch the error, right? And we know it's either too small or too big. So if error is on blah 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 dot too small. Okay. If it's too small, we need to return 10. All right. Then if we get any other error, we should return that error. Otherwise, we return the U32 number. Okay, so I guess they tried to say if error is not null. How do we do any other error? Because here we always return error. Can we do return error catch? No. What the hell am I trying to do? The number here, right? If we get any other error, oh, wait a moment. We already are returning the normal thing here, right? We are already returning whatever we're supposed to. Only when there's error, we actually doing this. Okay, that makes sense. So we just return error. Okay, all right. And there we go. And CPN says that's the thing. You can return additional value along with error. Interesting. I mean, that makes it lightweight, but at the same time, sometimes you want the additional info, like actual value or maybe reference to something. Interesting. I guess if you want to return an error with something extra, that's a bad practice. Therefore, you need to handle errors ahead of time and maybe make it not into an error. I don't know. Very strange. I'm sure it's deliberate. Okay, Zig run 024 and it worked. All right, let's go to the last of errors for now. Zig has a handy try shortcut for this common error handling pattern. Can fail, catch, error. Well, if it's error, just return it, right? So which can be more compactly written as try can fail. All right, so we have this, my number error, bam. Main function, we have those three that will be 0 in case they're error, okay? And we just print them. So in this case, the add5 takes in a number. This function needs to return any error which might come back from detect. Please use a try statement rather than catch. So far we have that the x is detect n. And then return this. Well, we can do try detect n. And if detect and fails, try will just do, well, return ahead of time. There we go. That's it. Detect, of course, can return those errors. All right. All right. Zig run 025. Beautiful. That went fast. SPN says there is a way to return additional info on how it failed. Okay. Okay. I mean, we'll eventually get to that. I just know that in the book, we need to first go to project, then we have debugging, pointers, another project, unit tests, build system, and only then we have error handling. So we have several streams before we get to error handling. Because I don't think I also will manage to finish this project today, especially that, I'm doing those exercises, which are actually awesome to quickly remind me what we did last time, what we learned. So, hello 2. Great news! Now we know enough to understand a real Hello World program in Zig, one that uses the system standard out resource, which can fail. Okay, so take note that this main definition now returns error void rather than just void, since there's no specific error type. This means that Zig will infer the error type. Okay, so that's what it means, it just infers it. Okay, great. This is appropriate in the case of main, but can make function harder, as in function pointers, or even impossible to work with in a recursion in some situations. Okay, so sometimes we won't be able to define exactly what type is supposed to be returned as a type, as an error. So you can find more information at the official documentation. Great. So we have our public function main that can return an error or nothing. We get a writer for standard out so we can print to it. Yay, finally. So we have a standard out, we go to our standard file system, we get file, standard out. So that's just file number 1, at least on Linux, and the writer with options or something, I don't know, maybe. And unlike standard debug print, the standard out writer can fail with an error. We don't care what the error is, we want to be able to pass it up as a return value of main. We just learned of a single statement which can accomplish this, right? So we do try standard out. Yeah, standard out is our writer, right? Okay, so writer returns a writer, and it takes in file and a buffer. So I guess because this is dot, the file is the already provided, and buffer is some kind of buffer, and we don't provide it. Ampersand of what the heck was that? I forgot what that was, because we can do it to print and a few other areas. It was anonymous struct or something like that. Just a pointer to it, as in what, we don't have a buffer? Maybe that's what it means. We just straight up don't have a buffer. Yeah, 0 length thing. Position is more thread safe since global seek position is affected. Oh, it's position reading. Whatever. Okay, doesn't matter. There's too much detail right now. But okay, so we did try standard out dot interface print. That's interesting. What is interface? Just IO writer interface of the writer itself? Maybe. Print the hello world and some arguments and whatnot. Okay. CPN says when you return the additional info on how it failed, the error at least, people call it diagnostics pattern. Okay. And ampersand dot curly brackets, which is this thingy, means an empty slice there. Okay. All right. Empty slice makes sense. So we just don't give it a buffer. I guess use default or use no buffer. Just always print straight to the file. Maybe that's what it means. We don't have to flush. Okay, makes sense. Alrighty, so let's run it. I mean, let's save it first and let's do Zig run 026. There we go, hello world. Beautiful. Okay. So let's quickly go through the fur and maybe through switch and all the way to this quiz. And we're gonna finish for now. At least with those exercises, this is whatever. It will be another 10 exercises that we did. So you can assign some code to run after a block of code exits by deferring it with the first statement. Bam. An example above, run later, will run when the block is finished. So the code above will run in the following order. Run now and now, then run later. This feature seems strange at first, but we'll see how it could be useful in the next exercise. Right, so we have nothing crazy here. Without changing anything else, please add a defer statement to this code so that our program prints 1, 2. So we have 2, 1. So we can defer 2 to be printed after 1. I mean, at the end. So Zig run 027. There we go. 1, 2. Done. Next. Now that you know how defer works, let's do something more interesting with it. So we have our standard, we have main function. Animals is just a list of characters. Okay. For animals, so we iterate over those characters, print animal, and it's just gonna print a letter. Okay. Standard debug print, and we just print it. Okay. Wow. Oh, so the print animal will probably print something depending on the letter, right? This function is supposed to print an animal name in parentheses like goat, but we somehow need to print the end parentheses, even though this function can return in 4 different places. Yeah, oh, that's actually a really interesting use case. I mean, sure. I can see problems with that, but yeah, this is fun. Okay, so print, and we start our parentheses. This one would instantly close, and we do a bunch of stuff. And at the end, we have unknown, as in possibly of animal that wasn't in here. So we can just defer our closing parentheses at the end behind the unknown, just by throwing a defer keyword. Zig round 028. Oops. There we go. And last one is unknown because it was C, or we can do X, and then we do K, right? And we'll have 2 unknowns in the end, I believe. There we go. Unknown, and done. There we go. Now 029. And CPN says the ampersand is there to turn array into slice. Okay, thank you. That's very helpful. So many little quick things. There's a lot of syntax in Zig, to be honest. Another common problem is a block of code that could exist in multiple places due to an error, but that needs to do something before it exits, typically to do cleanup after itself. Okay, yep. An error defer is a defer that only runs if the block exits with an error. Okay, so when we basically return, so we know that try can fail, literally is return error. And I guess this will be triggered whenever we return any kind of error. So the cleanup function is called only if the try statement returns an error produced by can fail. So we've got this and that. We have our counter. We have our error type. Ooh, excuse me. Either get fail or inc fail. And then we have a function. We simply quit the entire program if we fail to get a number. So constant make number, cache return. And here, so we have basically 2 situations where we return, but we don't really return the error here. So what about this one? Because this one's just main. So make number is standard print getting number, and please make the failed message print only if the make number function exits with an error. So, oh, when the make number. So, okay, I see. So we don't care about this one. We're just calling it here. And this will need to do stuff. So fail. So we have our get number. This could fail, right? And increase number also could fail. So this would be what got, but we wouldn't even get to here if any of those fail. This could first, this could later, and whatnot. So we want to basically do error defer, and that will basically print a message that, hey, something failed before we even do something. I wonder if we can capture the error with the error defer. That would be even nicer if we could just capture it and do something with it. That would be super cool. Probably there's a way to do that, just not yet. Okay. CPN says there aren't many things when it comes to syntax. So far, it seems like there is a lot. But, I mean, for sure, way less than nym. Nym is just crazy. And you can't capture the error in error defer. Okay. A little bit too bad, but I guess works. Because I can see the situations where you want to do a specific cleanup depending on an error. But maybe at that point, you just want to embed it where it's supposed to be. All right. All right. So Zig run 029. Of course, I learned to, wow, type. Getting number, got 5, getting number, failed. Beautiful. So let's go through switch statements. The switch statement lets you match the possible values of an expression and perform a different action for each. So this switch, switch over players. If 1, do this. If 2, do that. Otherwise, anything else, the other number, we just call alert and return game error, too many players. There we go. Is equivalent to this if else. So if players is 1, do this. Otherwise, if players is 2, and otherwise that, right? So this is actually less lines, but this is way more readable. Okay, so we have language characters. Okay. We have just 4 numbers. So we iterate over the numbers. Each character is just C. And if character is 1, we send A. 2 and whatnot until we just do the alphabet, right? Switch statements must be exhaustive. There must be a match for every possible value. Please add an else to the switch to print a question mark when C is not one of the existing matches. Okay, so we do just else, right? And we can just do print the question mark. That's pretty much it. And therefore, we should see some kind of result. Like 42 won't match. So it will be ZIG. So it'll be Zig question mark. Okay. Zig run 30. There we go. Zig question mark. And CPN says you can write error defer or defer statements anywhere in the function. Okay, I guess, I mean, if you have it in if else block, it's block wise, so yeah, it won't be function wise anymore. So that's the not nice part. You can run it at the end. But no worries, it's just some constraint to get used to. Okay, so this was easy. Now we have 4 more exercises left. What's really nice is that you can use switch statements as an expression to return values. So constant A is switch over something, and you just return values without the return keyword. So we have again the same situation, and basically instead of doing this whole print this, print that, you can see how much copy paste we have here. So we can just say, you know what, the real character is switch over C, do a bunch of stuff, add an else, which will return the exclamation character. And that's it. And then we just print it once, and that's pretty much it. Now the C forces print to display the value of a character, about the value as a character. Can you guess what happens if you remove the C? Well, it will just print out the number itself because it's just a U8, it's just a number. So we'll be able to demonstrate that. Zig run 031. There we go. We got Zig exclamation mark. If we remove the C, it will be just a bunch of numbers, which are of course different than those because these are translated into different numbers. Okay, all right. So now let's just take a peek at unreachable. Zig has an unreachable statement. Use it when you want to tell the compiler that a branch of code should never be executed and that the mere act of reaching it is an error. Okay, all right. So I like that. Instead of just throw error or whatever, it's supposed to be unreachable. All right. And it's way clear to the compiler that or the reader of the code that, you know what, this is not just unfinished code, this is just not supposed to happen. So if true, we do that. Else is unreachable. You know, like we're not supposed to have false when we have true, right? Here we've made a little virtual machine that performs mathematical operations on a single numeric value. It looks great, but there's only one little problem. The switch statement doesn't cover every possible value of U8 number. We know there are only 3 operations, but Zig doesn't. Use the unreachable statement to make the switch complete. Or else. Alrighty. So operations, we have those. Alright, so we'll try those operations. So we basically have the current value and we iterate over operations. This is our operation as U8. If it's 1, do something. If it's 2, do this. If it's 3, do that, right? We modify the current value at every time. And then print, bam. So we can basically say, because we don't have that. So we know that use the unreachable statement to make the switch complete, right? Because right now when we try to run it, it will say like, you know what? You didn't cover all the U8 possible numbers in your switch statement. Zig run 032. There we go. Error, switch must handle all possibilities. So yeah, it doesn't. So let's do else and unreachable. I guess we can just do that, right? We don't need to start another block, I hope. Yeah, that's it. SPN says, by the way, you can also have for and while loop as an expression. Yep, I think I saw it somewhere. And then at that point, what was it that was returned in value? I don't remember. We saw something like that at some point, but I don't remember anymore. So we'll learn over time. But it's good to keep that in mind, definitely. Okay, and then we have if error. I wonder if there will be more about those for loops and whatnot. Comp time, async. Oof. Yeah, there will be another for loops and a bunch of stuff. All right. So we have stuff ahead of us. If error, let's revisit the very first error exercise. This time we're going to look at an error handling variation of the if statement. If foo is value, right? Foo was not an error. A value is the non-error value. Okay, so we just do if foo. And I guess the foo doesn't have to be true value. It just is a value, right? Otherwise, we catch the error. So foo was an error. Error is the error value of foo. Interesting. We'll take it even further and use a switch statement to handle the error types. Bam. So iterate over foo. value, and otherwise we can do error here. So that's our if statement, and we can just throw in a switch statement and continue on. Okay, I kind of like having this in one line. This is really nice. So if our number error again, too big or too small, we have our numbers and we iterate over the numbers. We print the number and then we basically try to get a number that could possibly fail, right? So if we got a number, we should get a value that's just any kind of U8. All right, so we can just get it here. I guess this syntax is triggered by having this part after the thing. Okay, makes sense. And then we just do something. And otherwise, we have an error and we can switch over which error. If it's too big, do stuff. Add a match for too small. Okay, so we do my number error, too small. And we can do, and have it print less than 4. There we go. That's done. And that's, but number may fail. This time we'll have number maybe fail, return an error union rather than a straight error. Okay. There we go. This way it's kind of clearer for the rest of the code to kind of figure it out. Okay, makes sense. But now I'm wondering, can I just skip this part and just do this? Because we saw that before. Can we just do this? Let's see what happens. Zig run 033. No, we cannot. Can we do this for the switch statement? No, we cannot. Too bad. Wonder why. I recall we saw somewhere where it was possible, huh? SBN says, I forgot to mention error handling can be done with if. Yep, there's a lot of ways to handle those errors. But they also are some kind of intuitive, so yeah, I like it so far. I'm sure there's some rules about skipping that when it's possible, when it's not. Oh well. Oh well. We'll learn over time. And now we have the last exercise for today, which is the quiz. Quiz time. See if you can make this program work. Solve this in any way you like. Just be sure the output is, my number is 42. So this needs to receive 42. So we have our standard import. Number error is error, and we can have only one value, illegal number. We have our main function that seems all right. Then we have standard out, standard blah blah writer. So we have our writer here. Oh, we will be doing this, right? We need to try it. Therefore, we need to consider the possibility of getting an error here, right? We could either leave the void and handle it somewhere here, but in this case, just, we can't see the file. We can get the file or print to it. That means we can't really do the basic function of the program, so we can just, stop the program with an error. No big deal. So now what? This should be fine, but we have our get number. What does this do? This function is obviously weird and non-functional, but you will not be changing it for this quiz. Okay, so we're not changing it, right? Because it could return error if... It could return error, but it won't. Okay, that's it. So Zig run 034 and get number. Oh, we need to try, right? Try, otherwise we just return error. I mean, we could kind of cheat and say, you know what, if this is error, just catch and just return 42, to just correct for it, because we really want 42. So yeah, no matter what, it's gonna return it. Okie dokie. Okay, so that's it for Ziglinks. we can probably close all and get back to our little exercise file, which is in a form of do not run. And we can get finally to our project. How long did it take? Nearly an hour of just signals. But hey, we got a decent refresher on various features that we read about. But it was so long ago that at least I was able to forget about them, at least about the details. So, all right, so what is the project? Project 1, building a base64 encoded decoder. As our first small project, I want to implement a base64 encoder decoder with you. Base64 is an encoding system which translates binary data to text. A big chunk of the web uses base64 to deliver binary data to systems that can only read text data. The most common example of a modern use case for base64 is essentially any email system like Gmail, Outlook, etc. Because email systems normally use a simple mail transfer protocol as an SMTP, which is a web protocol that supports only text data. So if you need for any reason to send a binary file, like for example a PDF or Excel file as an attachment in your email, these binary files are normally converted to base64. Wow, okay, what a waste. Before they are included with the SMTP message. So the base64 encoding is largely used in these email systems to include binary data into the SMTP message. Alrighty, sure. So how the base64 algorithm works? But how exactly does the algorithm behind the base64 encoding works? Let's discuss that. First, I will explain the base64 scale, which is a 64 character scale that is in the basis of the base64 encoding system. After that, I'll explain the algorithm behind the base64 encoder. Let's just get to the actual content instead of descriptions. So, the scale. The base64 encoding system is based on a scale that goes from 0 to 63, hence the name. Each index in the scale is represented by a character in its scale of 64 characters. So in order to convert some binary data to the base64 encoding, we need to convert each binary number to the corresponding character in this scale of 64 characters. The base64 scale starts with all ASCII uppercase letter A to Z, which represents the first 25 indexes in the scale, 0 to 25. After that, we have all ASCII lowercase letter A to Z, which represent the range from 26 to 51 in the scale. After that, we have the one-digit numbers 0 to 9, which represents the indexes from 52 to 61 in the scale. Finally, the last two indexes in the scale, 62 and 63, are represented by the characters plus and / respectively. These are the 64 characters that compose the base64 scale. The equals sign character is not part of the scale itself, but is a special character in the base64 encoding system. This character is used solely as a suffix to mark the end of the character sequence, or to mark the end of meaningful characters in the sequence. Okay. CPN says it only makes the dot like 1.13 times larger. No big deal. That is a lot of data, to be honest. If you have to transfer 1 terabyte, that's like extra 300 gigabytes. It is a lot. And the amount of emails that are being sent with random attachments and whatnot. Whoa, my chair recently broke. Now it's unstable. Alrighty. Yeah, I mean, it's just, in theory, it's not a lot, but 1.3 is just, in the grand scale of things, it is a lot. A lot and not a lot, depending on how you look at it. The bullet points below summarizes the base64 scale. Okay, so this is the thing. It's already suggesting various sets of ranges that we'll be able to apply some calculations to. Alrighty. Something tells me with comp time, we would be able to just make a nice lookup table and make it really, really fast. Okay, so creating the scale as a lookup. Oh, there we go. So we're doing lookup table. The best way to represent the scale is in code is to represent it as a lookup table. Lookup tables are a classic strategy in computer science to speed up calculations. The basic idea is to replace a runtime calculation, which can take a long time to be done, with a very basic array indexing operation. I wonder to what extent we're gonna do a lookup table, because we could do a lookup table for, like, those 64 characters, or we could make a lookup table for entire 256. But I think there's some extra math. But again, depending on how much you're doing that, lookup table could be way faster. If you have memory to spare, of course. And basic idea is just to replace a runtime calculation, which can take a long time to be done, with a basic array indexing operation. Instead of calculating the results every time you need them, you calculate all possible results at once, and then you store them in an array, which behaves like a table. Then every time you need to use one of the characters in the base64 scale, instead of using many resources to calculate the exact character to be used, you simply retrieve this character from the array where you stored all the possible characters in the base64 scale. We retrieve the character that we need directly from memory. And CPN says, I just invented my own more efficient encoding, lang by data. Example 3 QWE. Yeah, I mean, I believe there are already libraries that you can specify exactly how many character encoding you want, like base 12 or base 127. It will just do that for you. I saw those before. Oh, you mean that you basically say, oh, how many characters there are, and then the data. Yeah, I mean, yeah, it's just how some of the protocols are made, where you just literally couldn't represent any weird characters because they would be implemented in some way. It's just, you can think of that, when you're sending emails or whatnot, it's just divided on many things, and I guess it's easier to just do base64 than try to modify the existing protocol where you have million other systems already implementing them in some way. And it just got stuck to what it is now. Yeah. So we can start building a Zig struct to store our base64 encoder decoder logic. Okay, we start with the base64 struct below. Wow, we're going like straight into implementation. For now, we only have one single data member in the struct. For example, the member table, which represents our lookup table. So notice that we did it underscore table, right? We want to explicitly say that this is like a private thing, not public or something, which represents our lookup table. We also have an init method to create a new instance of base64 object, and a character at method, which is a get character at index x of type of function. Okay, so we have what? Our struct, we call it base64. We have the table, which is an array of 64 U8s. And we have a pointer here, so I don't remember what that was doing. Just don't remember. What the hell was that? Something with a pointer. It's a pointer to an array for some reason. Because what? Maybe we will be making it. I don't know. We'll see. Then we have public function init. So initialize will do what? Upper. Well, it defines upper characters, defines lowercase characters, defines the numbers. So they're all in order, or large, small, and whatnot. And then return a base64, which will be okay, so we create new base64. We set the table property to be this array plus this array plus this array. And because this is all constant, I guess, to some extent, we can simply say, hey, we should have indexes already taken care of. Yeah, everything taken care of. There we go. All right. This is much simpler than I initially expected. I expected there to be a little bit more logic, but yeah, this is just go for it, write them all yourself. Indexes will take care of themselves. Interesting. What I don't like is that this suggests that every instance of it has its own table. Because whenever we create this, I don't know, I'm unsure. Because from this is a constant. What, doesn't mean only that it doesn't change during runtime? I mean, this is constant base64 because we just define a type. So I don't know. Does it get run every time we run this, or does this array get reused? That's a good question. And Baba says hi. Oh wow. Let's back up a little bit. By the way, that underscore in table doesn't do anything. Yeah, I understand it doesn't do anything. It's just a convention probably to just say, hey, this internal thing, don't mess with it. Okay, Baba says hi, hello, and Baba is excited by CPN having a Clippy. Alrighty, which I read somewhere was some good cause, so awesome. Okay. And then we have get character at, whatever character at, which will be, we give it index use size, and we'll just return, we'll just return the equivalent of whatever. Let's say third character, it's supposed to be C. The 20 something will be somewhere here, right? Okay. In other words, the character at method is responsible for getting the character in the lookup table, for example, the table struct data members, that corresponds to a particular index in the base64 scale. So in example below, we know that the character that corresponds to the index 28 in the base64 scale is the character C. So we can just say base64, we initialize it, and then print character at index 28 is, and we just get the character at index 28, and that's it. No big deal. Again, that underscore, what the heck was up with that? Why? Huh? It just makes stuff ugly and unreadable. I don't understand that convention here. There we go. CPN says, we're everywhere, you can't escape it. I'm not trying to escape it. Alrighty, base64 encoder. So wait, just look up table, now the encoder. Something tells me this will be like really small. It's just too bad this project is not giving us anything to do. This is more of, here's how you do it. A base64 encoder. The algorithm behind a base64 encoder usually works on a window of 3 bytes. Because each byte has 8 bits, so 3 bytes forms a set of 8 times 3, 24 bits. This is desirable for the base64 algorithm because 24 bits is divisible by 6, which forms 24 by 6 as in 4 groups of 6 bits each. Therefore, the base64 algorithm works by converting 3 bytes at a time into 3 characters from the base64 scale. It keeps iterating through the input string 3 bytes at a time and converting them into the base64 scale, producing 4 characters per iteration. It keeps iterating and producing these new characters until it hits the end of the input string. Now you may think, what if you have a particular string that has a number of bytes that is not divisible by 3? What happens? For example, if you have a string that contains only 2 characters bytes, such as hi, Well, how would the algorithm behave in such a situation? You find the answer in figure 4.1. You can see that the string high, when converted to base 64, before it becomes string SGK equals. So we have original characters, H and I. Each one is converted to its decimal representation, right? Binary representation is this and that. So we're going to be doing binary stuff. Yay. A 6-bit transformation. Bam, bam, bam. And the rest is just null, right? 0, 0 here. And the rest one is like completely empty. So we just leave it empty. So that means that the decimal representation of the 6-bit is 18, 6, 36, and well, that's it. As GH, we just throw it through the lookup table, bam, 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 and we get out the equal sign. So, okay, I can see this is, all right. We're not really losing any data other than, you know, in this last character possibility case. Okay, all right. So taking the string high as an example, we have 2 bytes. So we like a full byte as an 8 bits to complete the window of 24 bits that the base64 algorithm likes to work on. The first thing that the algorithm does is to check how to divide the input bytes into a group of 6 bits. If the algorithm notices that there is a group of 6 bits that is not complete, meaning that this group contains n bits, where 0 is less than n bits, while n bits is less than 6. The algorithm simply adds extra zeros in this group to fill the space that it needs. And that's why figure 4.1, the third group after the 6-bit transformation, 2 extra zeros were added to fill the gap. And when we have a 6-bit group that is not completely full, like the third group, extra zeros are added to fill the gap. But what about when entire 6-bit group is empty, or it simply doesn't exist? This is the case of the fourth 6-bit group exposed at whatever, just shoulder. And this fourth group is necessary because the algorithm works on 4 groups of 6 bits, but the input string does not have enough bytes to create a fourth 6-bit group. Every time this happens, where the entire group of 6 bits is empty, this group becomes a padding group. Every padding group is mapped to the character equals, which represents null, or the end of meaningful characters in a sequence. Hence, every time the algorithm produces a padding group, this group is automatically mapped to equal sign. As another example, if you give the string, is it O or is it 0? Let's say it's O as input to base64 encoder. This string is translated into a base64 sequence MA equals equals. That is a lot for just one character, right? The character O is in binary. The sequence is 00110000. So with the 6-bit transformation exposed, transformation, this single character would produce these 2 6-bit groups, this one and this one. The remaining 2 6-bit groups become padding groups. Oh yeah, because those 2 zeros here actually matter. Those zeros are added because this is the first thing. So therefore, this needs to exist, this whole character. Even though it's 0, it will be just A, right? It will just become A, because that's just a bunch of zeros here. But we need those 2 zeros. The remaining 2 6-bit groups become padding groups. That is why the last 2 characters in the output sequence are this. And there will be never ever a situation where there's only one 6-bit group, because any character, that input character will be at least the 8 bytes. Or 8 bits, sorry. Alright. Makes sense. Relatively simple transformation, yet clever, right? CPN says, I might give an explanation on slice array and pointer to array later. Go ahead. That kind of writing where you try to explain some kind of concept in writing with examples, It's a fun way to realize if you actually understand the concept or not. Because when you start writing, it's like, oh, wait, what about this? What about that? What about that? How was this exactly achieved? All the edge cases are starting to spill out. Alrighty, so a base64 decoder. Okay, so we get, again, just theory, but let's see. The algorithm behind base64 decoders is actually the inverse process. Base64 decoder needs to translate base64 messages back to their original meaning, as in into the original sequence of binary data. A base64 decoder usually works on a window of 4 bytes because it wants to convert these 4 bytes back into the original sequence of 3 bytes. That was converted into 4 groups of 6 bits in a base64 decoder. Remember, a base64 decoder, in a base64 decoder, we are essentially reverting the process. Each byte in the input string, the base64 encoded string, the base64 encoded string, normally contributes to recreate 2 different bytes in the output. The original binary data, in other words, each byte that comes out of base64 decoder is created by merging 2 different bytes and input together. You can visualize this relationship in figure 4.2. So we have so this is our high. SGK equals. We transform them into those 6 bytes binary representation. Oh no, these are actually full binary representations that then we somehow merge, right? Into so all those 3. Some bit shifting and additions, right? Will end up being the actual 1 0 0 1 0 1 0 0 and an extra 0. Okay, I am confused, but what the hell? We got this and that and this and that. And this is all because the extra 2 zeros at the end were added kind of magically to get to the point, or maybe in the beginning. Here I think they mean at the end, right? Yeah, at the end were added. Okay, so just ones were added, not zeros. So we have this up to 0 0, and then we go from here 0 1, which is not what I expected. Why am I so confused? 72. We had this with 2 zeros. Well, S is something else. 0 1 0 1 0 0. 0 1 0 0 1 0. Okay, this does not translate to what was there at all. Those numbers are completely different. So I'll allow myself to ignore it. Is it at least the same as it was here? Yes, and yes. So these are correct, but this kind of gets me confused. Yeah, so we basically turn those 3 bytes into 2 bytes, and then we convert them back into actual letters. The exact transformations or the exact steps applied to each byte from the input to transform them into the bytes of output are a bit tricky to visualize in a figure like this. Because of that, I have summarized these transformations as some bit shifting and additions in the figure. These transformations will be described in depth later. Okay, besides that, if you look again, you will notice that the character equals was completely ignored by the algorithm. Remember, this is just a special character that marks the end of meaningful characters in the base64 sequence. So every equals character in base64 encoded sequence should be ignored by base64 decoder. Yep. And CPN is not enjoying this thing. Base64 hurting brain, right? Sounds weird. Okay, let's just move on. Difference between encode and decode. If you don't have any previous experience with base64, you might not understand the differences between encode and decode. Essentially, in the terms of encode and decode, here have the exact same meaning as they have in the field of encryption. For example, they mean the same thing as encode and decode in hashing algorithms. Thus, encode means that we want to encode, or in other words, we want to translate some message into the base64 encoding system. We want to produce the sequence of base64 characters that represent this original message in the base64 encoding system. In contrast, decode represents the inverse process. We want to decode, or in other words, translate a base64 message back to its original content. So in this process, we get a sequence of base64 characters as an input and produce output, the binary data that is represented by this sequence of base64 characters. Yep. And a base64 library is normally composed of these two parts. First, the encoder, which is a function that encodes, as in converts on a sequence. Yeah, it encodes, great. And two, the decoder, which is a function that just decodes. Yep, back to original data. Great. I'm skipping some of those explanations because they're just repeat, and just add confusion by just massive number of unnecessary words. Alrighty. Calculating the size of the output. One task that we need to do is to calculate how much space we need to reserve for the output, both of the encoder and decoder. This is simple math and it can be done easily in Zig because every array has its length. Its number of elements easily accessible by consulting the .len property of the array. For the encoder, the logic is the following. For each 3 bytes that we find in the input, 4 new bytes are created in the output. So we take the number of bytes in the input, divided by 3, use a ceiling function, then we multiply the result by 4. That way we get the total number of bytes that will be produced by the encoder in its output. The calc encode length function below encapsulates this logic. Inside this function, we take the length of the input array, we divide it by 3, and apply a ceiling operation over the results by using the divide ceiling function from the Zig standard library. Okay. Lastly, multiply the result by 4 to get the answer we need. Yeah, okay, makes sense. Also, you might have noticed that if the input length is less than 3 bytes, then the output length of the encoder is always 4 bytes. This is the case for every input with less than 3 bytes because, as I described in section whatever, the algorithm always produces enough padding groups in the end results to complete the 4 bytes window. It just adds those equal signs. So let's look. So function calculate encode length. We get the slice that will represent the input. And we want to return usize, but with an option of an error. There we go. And now we at least know what it means. At this stage here, we wouldn't. We don't know that there isn't even a concept of an error. Like, come on, throw a small chapter about errors. So, if input length is less than 3, right? If we have less than 3 characters as an input, we know that this is just going to be one group, so just return 4 and we're done. But otherwise, if we have more, we need to calculate how many groups of those 4s we need. So we just do, hey, you know what? Let's divide the input length by 3, right? Because 3 characters produce 4 ultimately. So we divide it into groups of 3, and we use this standard math divide ceiling. So I guess this is to divide integers where we just round it up in one go, which is kind of fun. And then we just multiply it times 4, and that's it. That's how we always ensure that it's divisible by 4. Alrighty. Now the logic to calculate the length of the output from the decoder is a little bit more complicated. But it's basically just the inverse logic that we've used for the encoder. For each 4 bytes in the input, 3 bytes will be produced in the output of the decoder. However, this time we need to take the equal characters into account, which is always ignored by the decoder, as we described in section whatnot. In essence, we take the length of the input and divide it by 4. Then we apply a floor function on the result. Then we multiply the result by 3. And then we subtract from the result how much times the character equals is found in the input. Exactly, because those equals were just added and they're not needed. The function calculate the code length exposed below summarizes this logic that we described. So let's just take a look. The code length. So we input again an array. So this time input will be the actual encoded string, right? So we basically, you know what? If it's less than 4 characters, we just return a group of 3 for some reason, right? If we have less than 4 characters, that sounds like an error. We should have 4 characters. Because less characters could be where we assume that the other ones are just equals and equals. And for some reason, they were skipped here when we provided the string, right? And therefore, we just don't need to even subtract anything. Just return 3. And I don't know, it's kind of weird. Then we have n groups, which means that we divide by 4 to see how many sets of 3 we will need eventually. And then, yeah, times 3, there we go. And of course, if we did the other ceiling, this one we divide floor. CBN says, fun fact, there's a reminder after the integer division, the program will just crash. If there's a reminder after the integer division, the program will crash. Okay. As in, if you try to just divide integers normally without converting them into float, is that even possible? Don't know, but okay. All right. And that's why we use divide floor or whatnot, or multiply. No, this will divide ceiling to avoid that problem when we try to convert divide it in strange ways. Okay, and then basically I is use size input length -1. And then we iterate over stuff, just removing the equal signs from the end. Okay. I'm not going deep into what exactly is doing here. Code is simple, it's just logic is not fun. Building the encoder logic. In this section, we can start building the logic behind the encode function, which will be responsible for encoding messages into base64 encoding system. If you are an anxious person and you want to see how the full source code of the implementation for this base64 encoded decoder, you can find it at the Zig examples folder at the official repository of this book. Great. So, not sure if that's the best project to just introduce, like, hey, you're gonna use some of those features that we just talked about. It's just you're gonna implement something that's inherently confusing in the beginning because it's a bit math and whatnot. What the hell? You have to, CPN says you have to do this with div trunk to truncate instead of x divided by y, or divide ceiling and divide floor. Yep. What's the difference between div trunk versus div floor? Oh, probably div floor handles negative values differently. I wonder. Okay. decoder logic. Alrighty. So the 6-bit transformation. The 6-bit transformation presented in figure 4.1 is the core part of the base64 encoder algorithm. By understanding how this transformation is made in code, the rest of the algorithm becomes much simpler to comprehend. In essence, the 6-bit transformation is made with the help of bitwise operators. Bitwise operators are essential to any type of low-level operation that is done at the bit level. For the specific case of the base64 algorithm, the operators bit shift to the left and bit shift to the right and bitwise AND are used. They are the core solution for the 6-bit transformation. So I guess we use shifting to left and right to position stuff correctly, and ampersand just to what do you call it? Just apply a mask that, hey, we care only about those specific bytes. And I guess that's what they're doing here. There are 3 different scenarios that we need to take into account in this transformation. First, is the perfect scenario where we have the perfect window of 3 bytes to work on. Second, we have a scenario where we have a window of only 2 bytes to work with. And last, we have a scenario where we have a window of 1 single byte. Exactly. In each of these 3 scenarios, the 6-bit transformation works a bit differently. To make the explanation easier, I will use the variable output to refer to the bytes in the output of the base64 encoder, and the variable input to refer to the bytes in the input of the encoder. So we're gonna get back to that in a second. I'll just gonna take a short little break. I'll be right back. All right, I'm back. Let me turn that thing off and we can continue. So maybe before we see exactly how this process works, I feel like we should go back and just copy paste some of the existing code so that we can keep track of it. and kind of start building it out and see what the LSP is telling us about it, right? So let's just copy this. We can go and just ignore everything else. Maybe I'll leave the standard. Okay, I'm gonna put this here and our main function. For now, we'll just say whatever, nothing. Whoa, I can't even spell that. So now we can see a little bit more clearly what's going on, right? We have our base64 as a struct. We have our table, whatever pointer here was about. We have our initialization, so we get our 26 characters here, 26 here, 12 here, and that adds up to, I guess, our 64, right? There we go. It's table is this plus that, and we can modify it to make it our own, which is fun. Okay, all right. So then character at simply returns the U8. We just get index, no big deal. So the next thing that we did, and CPS says, in div trunc, if the decimal section is more than or equal 0.5, it will round up to the value. And the opposite, okay, so div trunc is just div round. That's that. CPS says, whoa, new be right back screen. I think I did it on one of the Zig streams early. I just was like, you know what? I'll keep going somewhere for a second. I don't have any screen. I just disappear. When people go on a stream, they say like, "There's nobody here," so they just exit or whatnot. So I'll at least I threw that out there. So it was built on stream, 3 seconds in Figma. Yeah, whatever. Okay, so we got this. This was an example of what it could look like, but then we had the encoder and the coder, and we got a little snippet here. So calculate encode length, right? So something tells me this is inside that struct. Right? Not really. I mean, it's just static. It just doesn't operate on self. So I guess I could just throw it in here. I guess nothing bad would happen, right? And groups, try this and that. Wait a moment. This needs to have some proper indentation. There we go. Yeah, sure. Just throw it out there. We can also do that. And then we had the other way around. So that was encode, and decode was, as always, a little bit more involved. Why so little things in life can be actually symmetrical? Too bad. Okay, so we've got those two. Wow, this was really shortened. So in encoding, we just did that, returned that, and I believe we could just do it this way to kind of save up on lines. Try to do that, and although descriptors are making lines super long. And that's that. And then we've got a similar thing here. And we have that part, multiply, bam. And then we have the entire while loop for just a number of equal signs at the end. Okay, great. And that's that. All right. Great. So we can go back to our algorithm for how to actually start reversing those bits. And CPN says function names are supposed to be in camel case. Yep, I agree. Put a comma after the last parameter. Last parameter. I mean, there's nothing like divided into lines here. I don't want this. This looks ugly. Not sure what you're pointing at. Okay, so if you have the perfect window of 3 bytes, right, the best scenario, these are the steps for the 6-bit transformation. So output 0 is produced by moving the bits from input 0 to positions to the right. Okay, we're gonna move those to the right. I guess left side will be filled with zeros. So this is, let's say we have an example here where we would have something like bum 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 bum. Wait a moment. 4 and this is 4, right? We have something like this. We'll move it to the right, 2 of them. So we eat 2 from here, put zeros here, and we have the result somehow. I guess really what is happening, we're really eating from here and adding here. Something of this sort, because they're backwards or something. Don't know. To the right. Then input 1 is produced by summing 2 components. First, take the last 2 bits from input 0, then move them 4 positions to the left. Second, move the bits then, and then sum these 2 components to kind of add them up. Yep, so just, okay. In my head, it kind of makes sense. And output 2 is produced by summing 2 components. First, take the last 4 bits from this one, move them to here, and then the third one is, the fourth one really is produced by taking the last 6 bits from input 2. Okay, makes sense. Yeah, this is the perfect scenario where we have a full window of 3 bytes to work on. Just to make things as clear as possible, the figure 4.3 demonstrates visually how the step 2 mentioned above works. So the second byte in the output of the encoder is made by taking the first byte, dark purple, and then second byte, orange, from the input. You can see that at the end of the process, we get a new byte that contains the last 2 from the first byte. 1, 2, 3. Operations. First operation, we have A, B, C, D, E, F, G. Oh, I guess instead of binary, we just apply a mask to get 2 last only, right? We've got this one. We shifted 4, so we got this here. And then, yeah. Second operation is where we take this, shift 4. Oh, this is just presentation of several operations, right? We have and to mask stuff. We have shift left, we have shift right, which will just move them to the right. We fill with zeros again. And then we also have the third operation, which will be simply, add this one, because we have care about those bits on the left and those bits on the right. And when we sum them together, the zeros get ignored and everything else gets added in. Yep. Okay. Yep, that makes sense. And we just do like precise operations for each one of those numbers. So I don't know, sounds a little bit costly, but oh well, these are bitwise operations, they're fast. So on the other hand, we must be prepared for the instances where we do not have the perfect window of 3 bytes. If you have window of 2 bytes, then steps 3 and 4, which produces change a little bit and they become this. I'm gonna ignore that because this is kind of, you can get to that by yourself. Reading that just doesn't make any sense, and we have window single byte, we just take care of just those 2 things, and the rest are supposed to be charactered this, so they're zeros, and if not, whatever. If these bullet points were a bit confusing for you, you may find table 4.1 more intuitive. This table unifies all this logic into a simple table. Notice that this table also provides the exact expression in Zig that creates the corresponding byte in the output. Yay! Fun operations. Number of bytes in the window. Okay, so we have like 3 bytes, or maybe we have 2 bytes, or 1 byte, right? So byte index in the output will be 0. So the first byte will be just that. Just shift 2 to the right so that we have zeros filled in. Next one will be grab those. Yeah. So we basically see our bit shifts. We to left and right. We have our ampersands, our additions, and That's it. I'm not gonna go into that because I don't know what's the point of reading through that. It's just somebody thought how those operations are supposed to be performed, and they're just encoded, and that's it. NCPN agrees with me. This is not a good project to introduce a language. I 100% agree. It's like, what the hell? There are some nice aspects about this book, but the rest is just like outrageous. What the hell? I guess we need to write a better book. Oh dear, imagine how much time it would take. Okay, bit shifting in Zig. Bit shifting in Zig works similar to bit shifting in C. All bitwise operations that exist in C are available in Zig. Here in the base64 encoder, they are essential to produce the result we want. For those who are not familiar with these operators, they are operators that operate at the bit level of values. Now you're saying that? Really? This means that those operators take the bits that form the value you have and change them in some way. This automatically also changes the value itself because the binary representation of this value changes. And NCPN says, anyways, gotta go. See you later. See you later. Was good seeing you. Or whatever, having you here. We've already seen the effect produced by bit shift, but let's use the first byte in the output of the base64 encoder as another example. So we have just this shift. Okay, so it just goes over shifts. What a disappointing project. This is a truly disappointing project because we're not learning anything other than there are bit operations and that's it. If you recall your first byte, oh my goodness, selecting specific bits with the ampersand operator, yes, because it's a mask you apply. But again, this has nothing to do with the language. It's just like, yeah, let's introduce concepts and not explain them correctly. Or like too late, because I mean, if we're getting a tutorial about how each operator works, why did we have this whole thing that uses those operators for several paragraphs earlier? Sorry, I'm just really upset that this is done in this way. It just makes me mad. Allocating space for the output. Okay, so we have a little bit more here. So now we know how many characters to allocate. We know fixed length, the compile time. Well, we don't know. As I described, the store object on the stack, this object needs to have a known fixed length at compile time. This is an important limitation of our base64 encoder-decoder case because the size of the output from both the encoder and decoder depend directly on the size of the input. Having this in mind, we cannot know at compile time with which is the size of the output for both the encoder and decoder. So if we can't know the size of the output at compile time, this means we cannot store the output of both the encoder and decoder in the stack. Consequently, I mean, we could, anything in between we kind of could. Consequently, we need to store this output on a heap. And as I commented, in a section 315, we can only store objects in a heap using allocator objects. So one of the arguments, the arguments to both the encode and decode functions need to be an allocator object. Because we know for sure that at some point inside the body of these functions, we need to allocate space for the heap store to store output of these functions. Okay, so that's why both encode and decode functions that I present in this book have an argument called allocator, which receives an allocator object as input, identified by the standard memory allocator from the Zig standard library. Yep, so that we can just pass allocator to the to our encoding library, whatnot, and it will just allocate stuff, and that's it. And we just need to kind of free it afterwards. Okay, finally we're getting to the point where we're writing the encode function. Wow! Now that we have the basic understanding on how the bitwise operators work and how exactly they help us to achieve the results we want to achieve. Wait, help us to achieve the results we want to achieve. Okay, great. Buttery powder. We can now encapsulate all the logic that we have described in figure formula 1 and table formula 1 to a nice function that we can add to our base64 struct definition that we started in section whatever. You can find the encode function below. Notice that the first argument of this function is the base64 struct itself. Therefore, this argument clearly signals that this function is a method from the base64 struct. Because the encode function itself is fairly long, I intentionally omitted the base64 struct definition in the source code just for brevity reasons. So just remember that this function is a public function or a public method from the base64 struct. Furthermore, this encode function has two other arguments. Input is the sequence of characters that you want to encode in base64. And allocator is an allocator object to use in the necessary memory allocations. I described everything you need to know about allocators objects, so from the go, we read that, yep. By looking at the encode function, you will see that we use this allocator object to allocate enough memory to store the output of the encoding process. So let's just, we have more descriptions. Let's just look at the function. Okay, that's not too bad. So if our encode, it takes the cell base64, great. Let me actually just copy paste it into the whole thing and it will make a little bit more sense then. And we can read it a little bit more properly, I guess. Okay, alrighty. I don't like that. Just do it this way. There you go. There you go. There you go. And if you really need to, just go this way. Beautiful. Now it's easy to read all of them. And it's just one tab. Okay, so self, allocator, input, all that fun stuff. And we return we return either an error or a slice of U8. So if input length is 0, we return nothing, right? We can just take care of the whole thing. If there's nothing to the code, we encode nothing. Then we have our length, right? Calculate encode length of the input. There we go. We just try to do that. We have the number of characters. Then we allocate the memory for that. So we basically alloc U8 and how many bytes and out bytes. Okay. So at this point, our out is the slice. And then because our slice is kind of holds the pointer itself inside, we don't need to have it. We don't need to hold the pointer to it. We just can copy it around and we'll still point to the same place. We don't lose anything. And our buffer will be basically 3. Wait, so we are encoding, right? That means this will be 3 input characters in our buffer, okay? Count and I out. The hell is I out? And then we go over a loop where we loop over all the inputs, which are those. And whatever, we just track the index. We call index I. And basically in our buffer, we set the input here, right? The buffer count is, I guess we keep increasing that, right? We increase the count. Okay, so that's how we track which index we are supposed to. We just keep track of count instead of using something like modulo. I guess maybe this is faster. I don't know how many operations module takes. This is a good question to AI. Let's just do this in assembler. How many CPU cycles does it take to calculate modulo on integers? I'm trying to figure out what's faster. When iterating over an array. Basically, every iteration. Either recalculate the modulo every iteration, or store the value in a, what do you call it, variable outside the loop and increment every iteration. Let's see what it tells us. I'm really curious. How does module work on the back, on the back end and the assembler and actual processor? Because something tells me it's such a common use case that there will be like probably one CPU operation, right? The module operation on integers is significantly slower than incremented variable in assembly. Look at that, CPU cycle cost. So modular using div instruction on modern base64 processors, Intel Skylake, 20 to 80 cycles. Holy moly. And for 64-bit is even worse. Wow. Okay, I did not expect that. Zen 3 is nice and Cortex is even nicer. Wow. Wow. The wide range depends on the operand values. Division by powers of 2 can be optimized by the CPU and whatnot. So increment operation, just one cycle on virtually all modern CPUs. Okay. All right. So it's actually better to have a variable that you just keep incrementing. Avoid module at all cost. Okay. Lesson learned. Okay. Wow. So yeah, it's better to just keep track of that, especially that we keep reusing it in few spots. I mean, we just keep read it here. We check if it's 3 and that's it. And so basically, if we went and filled out the buffer, we go over and do our calculations, right? What's the character for 0, for 1, and for 2? And then not only we get the character, but we also do we do our buffer operations to calculate what number it's supposed to be, and then we get it out of the character. So these are the bitwise operations in here that we are not going into because it's just dark magic, let's say. It's just a waste of time to really focus on it right now. And yeah, I guess output, number of characters of the output is here. We just increment that to know that, oh, our output, we got to that point, and we count this. And probably at the end, after the whole loop, if we ended up at the count 1, we know that we still have one character in the what do you call it? We have still one character left in the buffer that we need to take care of. Otherwise, maybe we have 2 characters, right? And we do all that. We just fill out spaces with this. And what do we need this I out? Oh, to know where in the output to actually write. Okay, that makes sense. It's not like append. You just need to do it manually. Okay, and then we return the output. And our output is actually the thing that we allocated. So the user of our encode needs to remember to free it by themselves. Okay. All right. Makes sense. Okay, so this is not that bad. Encoding is not that bad. Decoding will be a little worse, but mostly in the characters in the bitwise operations probably. Okay. All right. So that makes sense. I don't think we need to read through that. It's kind of obvious. So now what about the decoder logic? Now we can focus on writing the base64 decoder logic. Remember from figure 4.2 that the base64 decoder does the inverse process of the encoder. Duh. So all we need to do is to write a decoder function that performs the inverse process. Yeah, it's not that simple. So mapping base64 characters to their indexes. One thing that we need to do in order to decode base64 encoded message is to calculate the index in the base64 scale for every base64 character that we encounter in the decoded input. Exactly. In other words, the decoder receives as as input a sequence of base64 characters. We need to translate this sequence of characters into a sequence of indexes. These indexes are the index of each character in the base64. So basically like the reverse of the existing array, right? There are probably better, faster ways to calculate this, especially using a divide and conquer type of strategy. But for now, I'm satisfied with a simple and brute force type of strategy. The character index function below contains this strategy. We are essentially looping through the lookup table with the base64 scale and comparing the characters we got from each character. Oh dear, wow, okay. I mean, it works, it's just not great. Notice that if the input character is equals, the function returns index 64, which is out of range in the scale. But as I described in section whatever the character equals does not belong to the character 64 scale itself as a special and meaningless character in base 64, so we basically will never look for it. Also notice that this character index function is a method from our base64 struct. Yep. So we have again character index, and yep, just search for them. Maybe you'll find one. Otherwise, just return out, and oh well, that's our equal sign, right? So the 6-bit transformation. So this is where all the fun magic with bitwise operations will go in again. So this is again going to be situations where we have 4 bytes, we need to produce 3 bytes, and therefore we need to do some more magic with bytes to actually get those values. I won't even go into that. We have more information about that. If someone is interested, just read the book. I don't care at this point. This exercise really pisses me off. Yeah. Don't show me bitwise logic. I'm not ready for that. Not tonight. Writing the decode function. The decode function below contains the entire decoding process. We first calculate the size of the output with the calc decode length. Then we allocate enough memory for this output. Yep. And 3 temporary variables are created: count to hold the window count in each iteration, the I out to hold the current index of the output, yet, and the buffer, which temporary buffer that holds the base64 indexes. So it'll be 4 of them. So I guess it'll be very simple, very similar, where we need to iterate over the input until we get like a full buffer of 4, so we can apply our full logic to convert it into 3 elements, just add them to the output, iterate, exactly. So we have the same thing. We have our output, basically our buffer of 4 elements. We iterate over the input, right? And we just keep adding until we finally get to the full count of 4. Our buffer is full. We can do our logic. So we fill out buffer 0. I mean, we'll have 3 operations to write with to the output, right? The first byte, the second byte, and the third byte, right? We written all 3. And at the end, we don't need to do anything else. Oh, because I guess our calculation further or whatnot basically made sure that we because we have our equal signs here. Considering we have our equal signs as the input, we already guarantee that it has proper length. Interesting. There was somewhere there that, we just ensure that we have proper length and whatnot. So yeah, we get to the results. Great. Now that we have both decode and encode implemented, we have fully functioning. So let's copy this and we'll at least try if it runs. If not, we're gonna search for what's wrong with it. But yeah, this is our decode. Let's just make it a little bit nicer. There we go. Beautiful. Yeah, pretty much the same thing. Okay. All right. So now that we have both implemented, we have fully functioning base64 encoder and decoder implemented in Zig. here's a usage example of our base64 struct with the encode and decode methods that we have implemented. So we have memory buffer. Oh, and we just use the fixed buffer allocator. Interesting. And allocator is allocator, right? Testing some stuff, eText, base64, encoded text, decoded text, whatnot. Where are we freeing it? Because we have buffer, we initialize the memory buffer on this, because we don't need to free it at all because this will get out of scope and free itself. That's why, I guess. Okay. What if you call allocator multiple times allocate? Because this encode will try it, and then have decode, which will try it again. Does it reuse it? I am so confused. I guess maybe in this case we just don't ever have a problem with that, but okay. So let me just do this. And we'll just throw it in here and see how bad it doesn't work. We have standard out print. Where does the standard out come from? We don't have it anywhere. We would need to get our writer, right? I know we can do constant. Std out is a standard dot file system dot I don't even remember how to write it. We had it somewhere in a recent Zig stuff, Zig links, quiz 4. Oh, it is file standard out writer. File standard out. So that's our specific file. We're just getting the file, which represents the by standard out dot writer. Okay, and there was this what ampersand dot this, I presume, anonymous struct with an ampersand in front of it to make it into a slice. Okay, and now we can do standard out print. There we go. It's just where do we need to make a test for it? Because this is writer. Oh, standard out interface print. Dot interface print. Apparently, at least that's what it says. So we'll try it. So what happens if I'm gonna do Zig run 000? Error struct. Struct declared here. Oh, wait. No field or member function name car index in here. Ooh, character index, character index. So I guess these two need to be, oh, I didn't put in this little funny one. There we go. With character at, we just don't have character index, the brute force one. There we go. Okay. All right. Now it should work. No, expected type IO writer file found constant IO writer. Try standard interface print encoded encoded text. Wait a moment. Arguments. Expected type IO writer while found constant IO writer. It cannot be constant. Do we need to make a variable? Does it modify it? Yeah, it does modify it, huh? And looks like it works. Okay, the code works. That's great. I just want to look because I think this is the end. So maybe we can kind of do some fun stuff. We went through this, the end result. Yes, that's it. You can also see full source code here. So next thing will be debugging and whatnot. We're gonna leave it for the next one. I'm just gonna, I guess, finish early today. I just want to take a look at this thing that he did with brute force, right? Character index. Where we just take a character and we need to find it somewhere. For equals, we just return 64, but for everything else, we just search for it in the table. So if self character at this index is the same character, we break and we return the index. So basically what we're doing here, we're doing reverse lookup, right? If we have a table from side A to point to side B, we could in theory just initialize reverse table, which will be literally the same thing, right? Because it's character pointing to character, a number to a number. Great. So in theory, if we have this here, the other thing will be to do, hey, reverse table is this thing. I don't think we have access to this thing in here yet, but how do we reverse it? I mean, we have to have basically the... Okay. So I wonder if we need to do it in a few steps. I don't understand this star in front of this here yet, because I feel like I could basically say that, hey, this thing is whatnot, and for returning it, we're going to modify it. But this is a constant. So something tells me we need to basically say, hey, there's a constant of 64 U8 or whatnot, and this needs to be what? Rev table of this type is... How do I initialize it now? That is fully initialized. I don't remember. Let's do variable, right? And this probably doesn't like the constant in front of it right now. How do we change it into constant afterwards? Because I have an idea how to perform the transformations. First, we need to have this table, then basically iterate over every element and just kind of swap them and assign to the new table. It's just, we need to have room for it first. So that's why I need this thing. And I guess this might be it. What if I'll just omit this part for now? And of course I can't. Ay, ay, ay. So we would need to basically take this. Okay. Dot, can I do dot map or something? No. How do you map over a list of over all elements of an array in Zig? I need an equivalent of this from TypeScript. Okay, let's just make something that I'm familiar with in TypeScript. So in TypeScript, I would have basically let rev array is bam. I'll say array of 64 elements. 0, 4 now. Okay. Then we have another line which we would basically say whatever I would say. Let, or more like constant array is like, you know, non-reversed array. So basically, you know, take the normal table, whatever array that of 64 elements. This. And then we're gonna have our operations. So rev array. No, we can't even do that. This would need to be something more interesting. So we basically for element. I mean, I know how to do for. Okay, let's take it maybe different way around. So let's say that we have our table, right? Our table is literally this. Bam. Does this have any type? Doesn't seem like. But for now we have the table, and reverse table needs to be whatever, the new thing. Which will be, I mean, this could be const. This could be var, which will be 64 of U8. Okay, that's all we need in theory. So this is happy. This one doesn't have a type for some reason. I guess I need to be explicit to say that this needs to be of, what was it? 64 of U8. Still don't know what that does because it looks like a pointer. We've got this one and that one. Beautiful. So now we're gonna basically go over all elements of a table to go through here. So for, and we go basically table. Do we need indexes? We don't need indexes at this point. We just want to go over the elements, right? Or no? We need the index. So it'll be from 0 to whatever. So we're gonna have table element and table index. Okay. And now we can do our reversals. So we basically need to do something like rev table, and instead of index, we'll do table element is table index. Why am I getting so confused? Okay, so that will be the reverse table, right? But now how do I copy it into this thing? Because this is going to create, again, this new thing. Well, here, in theory, I should be able to just do rev table. Which somehow shows up as constant again. What? How? How is this constant? Because I say it is, and I can turn variable into constant for some reason. It's probably not going to compile anyway. So let's just see what happens, what kind of errors we're going to get. Expected 64 array elements found 0. Oops, that's it. We need to kind of how do I make this array to actually have 64 elements? How do I make this array to actually have 64 elements? Zig language. Already creates an array of 64 elements. They're just all initialized to 0. No, it's not. I'm not doing that. Using array multiplicator. I guess I could do that. Comp time initialization. We can't do that yet. Runtime initialization does undefined. Okay, that's uninitialized. Okay, that's one thing. I think we could do that because this would just precompile it to be all zeros. We don't need zeros because we're going to set every single element ourselves. So let's try with the undefined. I kind of like this approach. So we can say that instead of putting it here, we're just going to do this thing. And we just do undefined. But something tells me it's going to fail here because it's going to say, sorry, this is different type. Yeah. Expected type U8 found U size. Ooh, that's right. So many problems. So when we are reversing this too, table element, here's U8, but this is expecting U size, while this is the reverse. Let's use chat. I feel we're going to learn some extra things thanks to that. So here's my code now. Okay. Just gonna give it this thing. It's good enough. The table L is U8, while table ID X is U size. Right? U size? Is it U size? Yeah. The rev table needs the opposite. How do I cast those types safely? There will be no, I mean, there's no possible situation. There is no possible situation of values, and either those two be larger than 63. Because that's a hint. We don't need to worry about like buffers and stuff. I mean, overflows and whatnot. So in Zig, you can use endcast to safely cast between integer types. So endcast will be just anything to anything. Really? Okay. And truncates the target by keeping only the lower bits. Okay. And as type correct coercion only works when types are compatible, so won't work from U size to U8. So really, it's suggested that I only do int cast for this one. I guess this one will figure it out on its own, right? The U8 to U size. Let's try it. Expected type const found this. Okay, so now we're getting finally to that point where it expects this while it's getting this thing. So what the hell? Let's just copy this whole thing. And maybe even do this. There we go. Here's my code. No. Let's just pretend that we have another closing thing here. So, and hello, Karlover, and Is CPN here? As far as I know, CPN is not here right now. How are we doing, Karlover, by the way? So I have this thing, and my error is currently this. I'm gonna paste the error of compilation and whatnot. All right. Let's just throw it in. And we can give it some extra explanation to our confusion. The thing is that the reverse table is expecting the star const. What was it? 64 U8. No idea what the star const is. I mean, const means that it's a constant, not changeable, so that's fine. But star means that, what, is a pointer? What the heck? While I create a simple bum 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 as var. How to make those compatible? I'm sure there are many ways. Can you present them and explain them in some detail? Let's see how could we really solve those problems, because I'm sure there's more than one way to approach it. As usually there is only. I mean, there's more than one way, right? So the issue is that this const means pointer to a const array of 64 U8. Yep, told you it's a pointer. While you're creating a regular array. Also, your ref table is a local variable that will be destroyed when init returns. Exactly. Here are the ways to fix it. Store array directly. Recommended. Instead of storing pointers, store the arrays themselves. Okay. I mean, I like that. Right? It kind of simplifies, I guess. And therefore we can just do, this is fine, this is all normal, we can just normal stuff. And this thing, the reference, this string literal. Oh, wait a moment. Oh, I understand now. Okay, because this is really a string, and this is a string, and this is a string. We're actually concatenating strings, that's right. And therefore, that's the problem here. So we can dereference it here, and there we go. Just put stuff in there. Okay, all right, that's one way to do it. And comp time initialization, most efficient, calculate everything in compile time. Yes, that's how I would love to do it, but we don't know yet. So we'll get to that at some point. Whoa, break here. Whoa. Interesting. Okay, let's not look at that yet. And global constants with pointers. So we have constant here, another constant. We can specify a constant here, right? So we don't need to recalculate it every time. And then in reverse table, we can just recalculate it and just throw it in here. But how is this? Oh, because it's comp time, that's why. Take address of local. Wrong, don't do this. Yeah. Okay, so, oh, this is nice. So yeah, this is array of 64 U8s. This is a pointer to a mutable array. This is pointer to an immutable array. This takes the address of an array and creates a pointer. And it's the references. Okay. So recommendation, use option 1, store arrays directly unless you have specific reason to use pointers. It's simpler, safer, and avoids indirection. So let's see what happens if we're actually going to try to do that, because something tells me the rest of the code is going to break. So we're going to say, you know what? No, we're just storing those arrays like that. That's it. Yeah, there we go. So now that means that our table is this. This is temporarily to go over things, but no, because this won't really do it. Huh. Can we just do something like this to kind of dereference it. I don't know. What happens now? Expected this, found that, so we're already doing well. All right, all right, all right. There we go, there we go, there we go. This shouldn't change, in theory. And now this one will be... Can we just do, say, table? It should copy values, right? In theory. We'll see. And then we have reverse table, and there we go. So notice that here in option 1, when we say this ref table, we don't need to do anything. It should be passed by copy instead of a pointer. So therefore this should work as well. So we calculate this once, use it, reuse it. There we go. Ugly, but it might work. So let's see if this compiles initially. Oh, there we go. Thread something panic, index out of bounds. Oof, yeah. Wow, okay. Ref table element. What? Indexes begin from this thing. Oh, that's right. This is more than just 64 characters. Oh, because those values might be larger. 256. Let's just cheat a little bit. How about that? Yeah. Let's just cheat a little bit. This should work. Okay. Oh, and the rest of the code seems to work. It doesn't care that this was like something that we would have to dereference and whatnot, so we don't have that problem. Okay. So in our decode now we're already using character index. If it's this, do that. Index is this, and here search for it. What if we're gonna say return self dot reverse table, and this will be the character. How about that? Let's see if it still works. It worked. There we go. We have it, in theory, way faster because we do this reverse stuff once. Okay, that wasn't that bad. Just a few things to simplify and, I don't know, learn a few things. Okay, that was simple. So I guess that will be it for tonight. I'm kind of getting tired. So, and those bitwise operations just made me angry. So next time, I guess we're gonna go through a rough idea presenting us with how to debug Zig applications, like print debugging, right? Debugging through debuggers. We'll see if something's gonna be recommended. As compile and debug mode, let's redebug program, right? Okay, all right, this is gonna be fun. And then we're gonna go to pointers and optionals, which will be longer, and I don't know how far we're gonna get, but it'll be good to know a little bit more about pointers and things like optionals. That sounds great. And building HTTP servers from scratch. What the hell? Implementing the server, creating socket objects, listening. Okay, this is gonna be another doozy. We're gonna see if we're gonna survive. If not, I'll be really upset with the book. But okay, that'll be it. So thank you so much for watching. It was fun at some points. So again, thank you for watching and see you next time.